Hi all, today we are going to discuss about different methods of producing the controlling torque in an indicating instrument. We have seen in the last class that the deflection system of most of the indicating instruments is mounted on the pivotal spindle. That pivoted spindle will be lying inside the jewel bearing. That is the most commonly used. So in such system, the control torque can be provided by using either spring control or using the gravity based control. So let us see each one of them. First I am starting with the spring control. So the spring control is the most common method of providing the control torque, that is TC, in electrical instruments. So in that case, the spiral hair spring, which is made up of non-magnetic materials like such as phosphor bronze, is attached to the moving system. So it is attached and it will be in such a way with the deflection of the pointer, the spring is twisted in the opposite direction and provide the required controlling torque. So let us take for example how this will work. This is the basic instrument. If you see from the top, the construction will be like this. So this is the permanent magnet. This is PMMC instrument, permanent magnet moving coil instruments. So this will be my magnet, permanent magnet. So inside the magnet there is a moving system. On this moving system there will be a moving coil. So here the springs will be used. This is the side view. You can see here the spring is visible. So this spring is used for producing the controlling torque, and deflecting torque will be produced by the coil which is wound on the rotor, and this coil will be used for producing the controlling torque. So how this spring will be wound? So the spring will be wound like this. Let us assume now the deflection is produced, because whenever the current is passed through the moving coil, the deflecting torque is produced, so the pointer will move. When the pointer is moved, because we know that the spindle will rotate, when the spindle is rotated, this spring will be tightened. That means the spring is twisted. Whenever the spring is twisted, it produces the controlling torque, because always spring want to come back to its normal position, because it will have the elasticity, it want to come back to its normal position. So as the angle is increasing, the amount of twisting increases, so automatically the control torque will goes on increasing. So practically if you take any instrument, generally two springs are used. One spring will be used in the top and another spring will be used in the bottom, and two springs are wound in the opposite direction. So one spring, let us assume, used in the clockwise, another spring will be in counterclockwise direction. The major purpose of winding them in opposite direction is to compensate for the effect of temperature. That is, whenever the temperature is changed or the temperature is increased, because we know that every metal will expand, so the spring also will expand, so the length of the spring will change. We are going to derive soon in this section only, because the amount of the torque that is produced will depend on the length. So when the length is changed, automatically torque is changed. So as both are wound in the opposite direction, so as the length is increased, for one spring it will be the tension, another side spring it will be compression. So because of this, the overall effect will nullify, because when they are wound in the opposite direction, the overall effect of temperature variations will be nullified. That is the major reason. So now coming to the spring, the bottom spring, one side of the spring will be connected to the spindle, and the second side of the spring will be connected to the pivot, because the pivot is the constant part which will not move, only spindle will move. That means when the spindle is moving, this will be either wound or unwound. So in both cases it will torque, because it want to come back to its normal position back. You agree with me? So now coming to the top spring, one side will be connected to the spindle and the second side of the spindle will be connected to a circular disc. It will be connected to a circular disc which is placed above this pivot. This circular disc, the purpose on this, there will be one screw will be provided. You can see here that circular disc is here. This is the circular disc here. So on this, you can see the extension is made. This you can clearly observe from the top view. The second side of this spring, is connected to this moving part. This moving part, you can see here this extra handle is provided. So this handle, there will be a screw, that screw goes in this handle. So by adjusting the position of this screw, we can adjust the position of this second side contact. That means we can adjust the second side contact by rotating this. That means by keeping some screwdriver here, if you are turning, so we can either twist or untwist your spring. So by that, we can adjust the tension in the spring. This is mainly used for zero adjustment. You can see here, for example, in this instrument, it is not showing zero reading. So it is coming below. So whenever the power is not given, it should show the zero reading. In order to do the zero adjustment, we have to adjust the tension of the spring, because with respect to time, due to fatigue, the spring decreases its strength, because the control torque will decrease. In order to adjust that one, we can adjust it by adjusting the by inserting a screwdriver here and turning this, automatically we can adjust the twist or untwisting of this one. We can control the tension of the spring. So for that purpose this will be used. I am repeating once again. So practically all the control torque that is produced by using two springs, both are wound in the opposite direction in order to compensate for the effect of temperature variations. And the top spring, particularly one side will be connected to the spindle and second side will be connected to a circular disc that is provided above the pivot, that you can see here. This is the one. So here that will have the extension and it will be like that. Outside we will provide some knob. By turning this knob, we can adjust the twisting or untwisting of the spring in order to make the zero adjustment. Because with respect to the time, there will be a fatigue in the spring. So because of that, the zero error may come. In order to adjust for the zero error, so for that purpose, this will be useful. So coming to the lower spring, one side will be connected to the spindle and second side will be connected to the pivot, which is fixed, which is not movable. So coming to the spring, generally practically, the spring will be like this. So rectangular type of spring is used. The spring is wound like this. Let us assume the thickness of this spring, this helical spring I am representing by T. And if you are seeing from the side view, because the thickness is this one, from the side view, let us assume the breadth of this spring is this much. From seeing from the front view, the depth or the breadth of this spring I am representing by B. So in that case, what will be the torque that we are going to derive? Let us try to summarize it. To give the controlling torque proportional to the angle of the deflection of the moving system, the number of turns on this spring should be fairly large, so that the deflection per unit length will be small. So if the deflection is more in the spring, that means if you are twisting the spring more, there is a chance that fatigue may come in the spring or the spring may spoil and it will lose its elasticity property. In order to avoid that problem and in order to make the controlling torque is proportional to the angle theta, the length should be very large so that the deflection per unit length or the twist per unit length will be very small. So that is done. So practically if you are taking the spring, this is my thickness T and B indicates the breadth of the spring, then in that case the controlling torque provided is given by EB T cube by 12L into theta Newton meters, where E is the Young's modulus of the spring material, which is in Newtons per meter square. B is the width of the spring. Width of the spring when you are seeing from the front view, because this is the top view, when you are seeing from the front view, the breadth will be visible. So that is the breadth of the spring is given in meters, and T is the thickness of the spring given in meters, and L is the length of the spring in meters. So when you elongate the spring, how much is the length? So theta is the angular deflection. Remember that it is in radians, not in degrees. You have to remember while solving the numerical. So as practically once the spring is designed, we know that E, B, T and L are constant for a particular spring. So we can tell the controlling torque is equal to some constant K times of theta, where K is equal to EB T cube by 12L. So this is called as the spring constant or control constant, or also called as restoring constant sometimes. So this stress in the spring must be well below the elastic limit of the spring even at the maximum deflection position, such that there is no permanent set or inelastic yield. That means it will not spoil its elasticity. For that, what we have to do? We have to increase the length of the spring so that twisting will not be more. That is one thing we have to do. And along with that, we have to take care that even after taking care that much, the maximum fiber stress should be always less than the allowable stress. So the maximum fiber stress is given by 6 into Tc by Bt square Newtons per meter square. So substituting the equation number 1, the value of Tc from equation number 1, we know Tc is equal to EB T cube by 12L into theta. When I substitute it and simplify, I will get the value of small l divided by T. This small l will come here, T cube T square. Square will cancel, T will remain. So L by T will be equal to E by F maximum into theta divided by 2. Let us take it as equation number 4. So this F maximum is the maximum fiber stress that is allowed. Always I want my stress should be less than this one. That means the maximum stress that is impressed on our spring should be less than maximum permitted stress, or otherwise the value of L by T should be as maximum as possible. It should be greater than when you substitute the maximum F here. So to understand this, I am taking one example. For the phosphorus bronze, the maximum allowable stress F maximum is equal to 30 meganewtons per meter square and Young's modulus is equal to 120 giganewtons per meter square. So from this, if you substitute, L by T will be equal to 120 into 9 by 30 into 6 into theta by 2, or we can get it as a 2000 times of theta. Let us assume the full scale deflection will come when the theta is equal to 90 degrees. It can be any angle, 0 to 90 degrees. Let us assume it is equal to 90 degrees. So when you are substituting theta is equal to pi by 2, because we have to substitute in radians, so L by T will come as 3140. So it is coming as 3140 when you are substituting this F maximum as maximum permissible value. But practically this F maximum impressed should be less than this value. That means this denominator is decreased. What will happen to the ratio of L by T? L by T will increase. That's why we can tell that to avoid the overstress, always F should be less than F maximum, or we can tell that small L by T should be greater than 3140 in this example. So now the controlling torque is produced. That means as the deflection is increasing, as the pointer is moving, that deflecting torque will goes on increasing with respect to the theta. So the pointer will come to the rest at a position when TC is equal to TD. So if you are taking, for example, for PMMC type of instrument, the deflecting torque is proportional to the current, or we can tell that TD is equal to some constant times of the current I. So at final deflection position, we can tell that TC is equal to TD. So we can equate both. That means K theta, that is the controlling torque, is equal to K2 into I, or theta is equal to K2 by K into I. Agree with me? Or from this I can tell that theta is proportional to the current. That means whatever the deflection angle is there, it is proportional to the input current only, the current to be measured. So because as a result of this, the scale will be uniform for the PMMC instrument with spring control. Whereas if you are going for the gravity control, we are going to see that it will be non-uniform. So before proceeding, let us see what are the properties of the spring that is required. First thing is it should be non-magnetic, so that it will not affect the remaining parameters, and it should not subject to much fatigue to avoid the permanent set. So that's why it is made up of pass branch, that is the best material for this one. And for instrument in which springs are used to lead the current in or out of the instrument. Like example of such instrument is PMMC instrument and dynamometer type instrument, because the current will pass through this spring only. So the spring should be able to carry that current. That is the first thing. And second one, as the current is passing through the spring, it should have the minimum possible resistance, so that the drop in this the spring should be minimum. That's why it should have the less resistance, and also it should have less temperature coefficient of resistance. That means when the temperature is changing also, its resistance should not change more with respect to change in the temperature. So in such cases, that means for PMMC instrument or dynamometer type, a special bronze alloy having low resistances are used. In other cases, we can go for phosphor bronze material. Getting it? So now coming to the advantages and disadvantages. So first one is the leveling of the instrument is not required if the moving parts are balanced. So what is the meaning of the leveling? We are going to see in the gravity control. There you will understand in detail. And the second one, in some instruments, example PMMC and dynamometer type instrument, they also serve as the current leads to the moving coil. It will carry the current to the moving coil, which is placed on the rotor. So for instruments whose deflecting torque is uniform, it provides a uniform scale, because we know the theta is proportional to the deflecting torque. If deflecting torque is uniform or deflecting torque is proportional to current, then theta will be proportional to current, or it becomes a uniform scale. That is the advantage of this one. So practically there is no increase in the weight of the moving system, because I have told in the last class, whichever the moving system, it should be designed in such a way the weight should be minimum and the friction should be minimum, so that the amount of torque required will be less, or the loading on the system will be less. So in this case, because the helical springs, these springs are very lightweight, so extra weight introduced by these springs is negligibly small. So that is the advantage of this one. Whereas we are going to see in the case of gravity control, the weight increases drastically. That is a disadvantage there. So now coming to the disadvantages of this instrument. So with the change in the temperature, the spring length changes, and hence the controlling torque also changes. So in order to avoid this problem, what we have to do? We have to use two springs instead of a single spring. With that, problem will be solved. And second one, the spring tension may change with respect to time. That means there is a fatigue with respect to time. With respect to the time, the property of the material changes. So because of this, the spring tension may change with respect to time. And the third disadvantage, one more thing is there which I have not mentioned here. If you want to change the controlling torque, you cannot change so much easily. You have to replace your spring. That is a disadvantage, because the length, breadth, everything is already fixed. So we cannot change the controlling torque easily, that much easily. So coming to the gravity control, in the case of gravity control, this is based on the gravity. So in this case, what will be there? There will be a control weight. So please don't confuse with the balance weight. This balance weight will be used even in the case of spring control also. This balance weight is used because whenever you are designing any instrument, we have seen that the pointer which is in the form of the wedge shaped. So let me go back. So I will show you there. So you can, I have told you that this pivot will be in this shape, L shape, and this pointer also will be in this form. This spindle will be in this shape. So entire weight is falling at this point. Entire weight is falling at this point. So always we have to take care that the overall weight or center of weight of your entire moving system should fall in the center, so that all the weight will fall at this point only. If the center of weight is not coinciding on this line, then automatically what happens? It will try to pull this system to some side. So because of that, your moving system may damage. So in order to make the center of weight to lie in the center of the line, so we always go for a balance weight. It is used for producing the control torque using the spring control also. So I am proceeding further. So this balance weight will be very less value. So neglect the effect of this balance weight when it is moving. So now coming to the control weight, the weight of this weight will be more. And second one, we can adjust the length from the center. From this center, how much is the far of this control weight? That can be easily adjusted. Here screws will be there. We can turn it and adjust the position. That will be the advantage. So now under normal position, so if I am taking the normal position, let us assume this is my spindle. So for this the weight is there. So this is my weight. So this weight, entire weight will act in this direction. So under normal position, or when the angle theta is equal to 0, case, the weight is acting below, and already it is lying below because it is only pulling below, so it is in the stable position. Let us assume the angle is changed. That means the pointer is moved from this 0 position to that position, some position. So what will happen? Because of the gravity, because you can see the weight is acting downwards. So as the weight is acting downwards, it want to come back to its position, this position. So what it will do, a torque will be exerted at this point so that it will spring back to its normal position. So if you are observing properly, when the value of theta is equal to 90 degrees, when theta is equal to 90 degrees, so the weight will be here, agree with me. So when the weight is here, the weight is acting like this. So the weight is acting like this. So under this condition, the amount of torque that is exerted or the pull that is exerted will be maximum. And when theta is equal to 0, the amount of torque or force exerted will be 0. Agree with me? Or we can represent this relationship in such a way. Let us assume with respect to the spindle, it is moved by an angle of theta. So this is theta, again we can extend here, this angle is theta, this is my W. So the component that is pulling this back to this position, I can represent as a W sine theta. You can see here when theta is equal to 0, the controlling torque will be equal to 0. When theta is equal to 90 degrees, the control torque is maximum. Agree with me? At this position, it will exert the maximum force to come back. And at this position it is 0. So I can represent that relation by sine theta. When theta is equal to 90 degrees, it is W. When theta is equal to 0, it is 0. So that is given by theta, and it is acting at a length L. If you want to calculate the torque exerted by this weight, so we can represent by W sine theta multiplied by the length. You have seen the torque equation in physics. So torque will be equal to W sine theta multiplied by L. The component of W in this direction or tangent to the circle that is traced by this weight when it is moving. So that will be W sine theta multiplied by length, or otherwise we can tell that WL sine theta. Generally the weight is fixed, and let us assume we have fixed the position L, then we can tell that this is nothing but some constant multiplied by sine theta, where WL is equal to constant. So if you want to adjust the value of the controlling torque, how can I adjust the value? Either by changing the weight, or second option by changing the length, by changing the position from the center. Weight cannot be changed easily, but the position can be easily changed by adjusting the screws. So that way flexibly we can control the value of the controlling torque. That is the advantage of this system. Getting it? So I am proceeding further. So Tc is proportional to sine theta. At the final deflection position, Tc will be equal to Td. That means kg sine theta will be equal to Td, or otherwise theta will be equal to sine inverse of Td divided by kg. So let us take for example of PMMC type of instrument where deflecting torque is equal to some constant type of current. So we can tell that theta will be equal to sine inverse of K2 by kg times of I. You can see here there is no linear relationship between the current and theta. The deflection is proportional to sine inverse of some constant time of the current. So that's why in this case the scale will be non-uniform. So generally the scale we are going to see in the next class. I will derive some numericals. I will solve 2-3 numericals. This concept will be clear to you. The scale will be cramped, that is compressed or crowded at the lower end. If you are taking the scale, the meter can read from 0 to 70, let us assume amperes. So in this case, 0 to 10 you can see it is just by moving a small distance only 10 is coming. Then the distance will between the two adjacent for the same value will goes on increasing. You can see here the scale is cramped or crowded. As you are going, it goes on expanding. So this is the case for gravity control. So let us see what are the advantages and disadvantages. The advantage is it is cheaper than the spring control because simple weight will be there. Helical spring is very costly, and it is unaffected by the temperature variations because weight is unaffected. And second one, it is not subjected to fatigue. It will not change with respect to the time, and the controlling torque can be easily changed by adjusting the position of this controlling weight. But there is a disadvantage. The instrument has to be used in vertical position only. It should be always used in the vertical position only. That means when the angle theta is equal to 0, at that condition this control weight should be vertically downwards. Otherwise it will create the error. So that is a major limitation of this instrument. That means we cannot use it for practical instruments where we go and handle here and there. This can be only used in the case where it is a wall mounted instruments where the position is fixed and they always operate in the vertical position. Only in that case we can go for this instrument. And second one, the weight of the moving system is more due to this controlling weight. So automatically the loading on the system will be more because it will draw more power to produce the required deflecting torque. And next one is they have non-uniform scale. So these are the limitations of gravity control. That's why in practice we always go for the spring control only for most of the cases. So I hope the different types of the control torque, how they are produced, are clear to you. So we will solve 2-3 numericals in the next class so that this concept will be completely clear to you. So I hope everything is clear. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.